Okay, we have started to review some terms in probability because probability is playing a very important role when we are dealing with pattern recognition. Because in pattern recognition, when you try to recognize some pattern or when you try to find some cluster, we are dealing with some probability. So making some probability model is playing a very important role, as you have seen already and you will see afterwards. Now today, we have talked about the distributions. We said that we have different type of distribution. We could model things with this type of distribution. Today we will learn how we can discriminate between these type of distribution. Because imagine for each pattern you manage to have a very good model. Now the question is that how we can use this model in order to discriminate between the patterns. This is the whole aim at the end of the day, isn't it? So there exists several ways of looking at this discrimination. Easy way is looking at the mean value. We have sets of numbers. We see that, okay, the mean of this set is 10, the mean of the other set is 20, so they have the mean of maybe another set is some other number. So we look at the means in order to discriminate them. But it's pretty weak, isn't it? Another thing is variance and the standard deviation. Mean gives us some meaning, but a very important thing is that they talk about how far we can go from this mean. Variance, the meaning of variance is that how much we are varying around the mean. Now, which one is better, big variance or small variance? The small variance shows how precise and accurate we are. We prefer to have very small variance because it shows we can have the points that we have are very close to each other. In other words, the within class distance will be very small if we have very small variance. I'm sure you are very familiar with the concept of mean and with the concept of variance, so we don't talk about them as you know it. Now, we will talk about covariance, correlation coefficient, and moments in today's lecture. Covariance means that we have several assets, several events, and we want to know if these events are happening the way that they come together or they go away from each other. Now, we see the formula for covariance, but in general, in pattern recognition, we do not calculate the covariance because computer always calculates it for us. The formulation for covariance is defined as what you see in here. Expected value of the random variable x and y minus the mean of x multiplied by mean of y. Formula for expected value, again, it is available on probability books. You are not responsible for calculating any expected value. For us, computer calculates the expected value. What is very important? The properties that the covariance have. Because covariance can be calculated and it will result to a number. The important thing is how we can interpret this number. Now, if x and y are independent random variables, the covariance will be 0. Do you know why? What does it mean? Two random variables are independent.
One changes, it doesn't affect them.
Exactly. Today you wear a blue shirt and me have a cup of tea in the morning. They are irrelevant. So they are independent. So it means that occurrence of one does not depend on occurrence of the other one. In other words, the mean, the probability of having this event happening is irrelevant and independent from the probability of the other event happening. So it means the mean of x and y happening at the same time is mean of x multiplied by mean of y because they are irrelevant from each other. Now, so if x and y are independent, it means that exy is, if I have a pen, if x and y are independent, expected value or mean of exy is ex multiplied by EY. EX is actually mu x, EY is mu y. So if x and y are independent, we have mu x multiplied by mu y minus mu x multiplied by mu y, which is 0. Which is 0. Now, another thing which is very important is this. If we add a number to our random variables that we have, and we calculate the covariance, nothing will be changed. If we are adding only number, look at A, look at C, forget about B and D, nothing will be changed, right? This means that if we have sets of data and you move them somewhere else, still you can have the same covariance and you can interpret the number. Maybe it's easier for you to move it from, let's say, a range of 100 and 101, and the other one is 150 and 155. You can move it to range of 0 and 1, and let's say 15 and 20. However, if you scale your variables, your random variables, you have to scale the result of the covariance. So covariance will not be changed if you do the translation, but if you are scaling, the covariance will be scaled accordingly. And if we calculate the covariance of a variable, random variable by itself, it will result into a variance. And the proof, again, you don't need to know the proof, but the proof is pretty simple. Covariance of x and x is the expected value of the first one multiplied by second one minus mu of the first one multiplied by mu of the second one, which is expected value of x squared minus mu x squared, which is the definition of variance of x. Which is the definition of variance of x. Now, I said covariance means that if we have, let's say, covariance of two random variables, two assets, two events, if we have them, while looking at the numbers, we can understand if they are happening in line with each other, if they are happening opposite of each other. So in general, we have the three possible situations. Positively big number, negatively big number, and 0. Now, we know that if it is 0, it means they are independent. There is no relation between them. One can happen independent from the other one. But if they are positively big number, we calculate the correlation and you see that it is very positive big number, it means that they are very in line with each other. They are very in line with each other. Like this will happen, the high probability this will also happen. Okay? Like if I don't come to the class, we don't have a class. So the probability of me not coming to the class and you don't have a class is very high. So they are very highly, if we calculate the covariance, it will be a very big number. Negatively big means that, now, again, they are related in an opposite order. They are related in an opposite order. It's similar to, if this happened, the other event will happen in the opposite direction. It's like that. We have two cars which are going in the same direction, in the same line, but in totally different directions. Now, many times, depends on your scenario, many times we consider the absolute value. The absolute value, the direction sometimes is not very important for us. As well as we find that they have a strong relationship with each other, that is alright. Because if you know that the relationship is in opposite direction, still you can guess what should be the next one. You know, you can comment on the probability of the other event. The only situation we cannot really comment if something happens about the other one is when they are independent. Of course, when we have the probability course, we love this type of things when they are independent. Whole the line is very easy, you can calculate them separately from each other. Now, there is a formula which relates actually variance and covariance together, and it is for the sake of reminding you. If we are adding two variables two random variables, the variance of this addition is variance of the first one plus the variance of the second one plus 2 multiplied by covariance of x and y. Now, variance of x minus y is variance of x plus variance of y minus 2 covariance of x and y. That's why that maybe you remember in the probability course, you might have this relationship. If x and y are independent, then variance of x plus y is equal to variance of x minus y is equal to variance of x plus variance of y. Why? Yes, because the covariances are 0, so you can see that the terms are equal to each other in case of independent random variable. Now, here we see the covariance matrix, how it is being calculated. We like to see covariance matrix, but again, if you are using MATLAB, let's say, or any computer language, with one line you can calculate the covariance matrix. What covariance matrix tells you, it tells you that what is the relation between, let's say, the variable on this row and the variable on this column. Here we continue by talking about what will happen if the random variables are independent. Now, what will happen if random variables are independent? In other words, xi and xj. If they are independent, what is the covariance value? It's 0. If I and j are not equal to each other, it is 0 because we had it here. If they are independent, it is 0. And if they are independent, it doesn't matter if they are independent or not. If both of them are the same, in other words, xi and xj, I is equal to j. What is the covariance? It is variance. So here in the covariance matrix, if xi's and xj's are independent, it means all the elements which are not on the main diagonal will be 0. This is the covariance, let's say, between x1 and x2, which is 0. Now, what about the main diagonal? What it is? It is the covariance of x1 by x1, x2 by x2. And we know that the covariance of x by x is actually variance. So, in case of linear independent, we know that all these elements will become 0, and as the diagonal matrix, we know the inverse of this covariance is pretty easy to calculate. Now, why I'm writing this? Because later when we are talking about distances, sometimes this covariance and inverse of covariance are being used in order to calculate some distances. Now, what we will do soon, we will talk about how, if we know the probabilities, if we know the statistic, how we can find the discrimination. In other words, how we can find the distances. You will see sets of formulas in here, but you don't need to memorize any of these formulas in the sense that if you are simulating anything or if you are writing an exam, you always have the formula in front of yourself. Important thing is you have to be able to analytically goes on looking at which of these distances will be more appropriate for your application. So lots of distances, lots of methods. The question is that which method is more appropriate. Now here we have a few more properties of covariance. Again, we will not deal with them because computer can always help us. Have you seen these formulas? I mean, is there anyone who has never taken any probability course, by the way? Okay. What happens is if we have a matrix A multiplied by our random variable plus a number, we know that plus a number is not changing anything in the variance, it's not changing anything in covariance. So ignore that one, but if we are multiplying our random variable with a matrix, it is like the result of the variant, the variance of the resultant will be like the variance of the x, which has been multiplied by A and A transpose. covariance of x and y. We know that covariance is a matrix. So if we calculated it for y and x, it will be the transpose version of the previous one. So changing the place will simply make it transpose. Now, here, as we were expecting to see, if we are multiplying by matrices, what happens to the covariance? We have to multiply the covariance with those matrices. Covariance has the probability of distributivity, which means that the covariance of x plus y and z is the same as covariance of x and z plus the covariance of y and z. Now, that was covariance, big matrices, lots of calculations. But we have something which is even much simpler and will give us the same results when we are looking for. Of course, different interpretation, but it gives us more or less the same results if we want to talk about if the random variables that we have are in the same line or they have the same intensity or not, And that is something which is called correlation coefficient. Now, correlation coefficient is calculated by covariance of x and y divided by a standard deviation of x multiplied by a standard deviation of y. Remember, sigma s squared is variance, sigma alone is the standard deviation. Now, rho, the correlation coefficient, is a number between -1 and 1. 1 means that they are exactly in the same direction, exactly the same similarity. And -1 means that they are same but in opposite direction. So negative means opposite direction, positive means they are in the same direction. And when it is 0, you don't comment. It means that they are not correlated with each other at all. Now, keeping things correlated is good because we can use it, for instance, in order to make one cluster out of them, because it means they are of the same behavior. And another important thing that we use when we want to talk about one set or compare it with several sets is something which is known as moment. Moment is calculated by using this formulation: expected value of x to power n is moment n. Some of these moments are very famous, like moment 1 is known as mean. Moment 2 is used in order to calculate the variance. So variance is second moment is not true. Variance can be calculated from second moment. We know that sigma x squared is moment 2 minus moment 1 squared. Now, I'm sure I have shown you some slides about some type of distributions. You know, uniform distribution, right? Exponential distribution. There is a type of distribution which is known as Gaussian distribution. We specify and we spend quite time on this type of distribution. And the reason behind it is that this is a very friendly distribution. We know a lot about this distribution, and this is type of distribution that happens a lot in the real life. So it makes it very strong. Another important thing is, as you notice, I have represented two terms in red and the rest in black. Do you know why? What is it about the black term and what is it about the red terms? The black terms are constant and the red ones are the ones which are variable. In other words, we can talk about the whole distribution by specifying what is mean and what is sigma. So the whole distribution, which we know a lot about it, can be only specified by two terms. Its mean and its variance or standard deviation. Now here you can see several examples what will happen if you are changing the mean and if you are changing the standard deviation. The blue one and the red one have the same standard deviation but different means. So we know that if we change mean, it means that the bend that we have, we are translating to the right and left. Do you know what is the effect of the variance? What will happen if I reduce the variance or I increase the variance? If I reduce the variance, this bell will come together and will become smaller and smaller. And if I make it big, the bell will become, or the hat, there are several names for them, it will become bigger and bigger. So it becomes wider. So as you can see in the green one, the standard deviation has been increased, so it will become wider. Now, one question. Do you know why this value has been dropped when we are comparing these two? You know the peak has been dropped. Do you know why?
It's the probability has to be.
Yes, this is a probability distribution function. The area under this should be 1. As you start to give more priority to the smaller values, more chance of accuracy, you have to reduce this one because the area should kept to be 1. Of course, you could try it by normalizing and then it will not be a probability distribution function. Now, mathematicians have spent huge amounts of time to talk and look at the properties of this type of distribution. You might remember, even in high school, we have this table of normal distribution or table of Gaussian distribution, which you look at some values and look at what is the area underneath the curve. In other words, the area underneath this curve is always known to us. And the area underneath this curve tells us what is the probability. Remember? You remember this one? And if this was a PDF, we were saying that this area, what is this? What is this? What does it represent? Probability of x is less than or equal to x0. So area is very important for us because it tells us what is the probability. We can have it like limited, we can have it right-handed, so we can always calculate it and the mathematicians can calculate it for us. Now, a few important things that we have to know. If this is the mean, if this line is the mean, plus minus sigma will make me to cover 68% of my data. So if I just go 1 sigma to the right from me or 1 sigma to the left, it means I have a 68% of the energy. I have the 68% of the probability of accuracy. And even better, if I go 2 sigma to right or 2 sigma to left, in other words, mu plus minus 2 sigma, I have 95.4, almost 96% of the whole data. And that is great because I can easily consider 96% of data and comment. Now, we know that this is a symmetric around the mean. This is a symmetric function around the mean. And these wings, the end part starts from minus infinity and goes to plus infinity. One of the very beautiful properties of this Gaussian distribution is this. If you are in time domain, if you are in the spatial domain and you look at something Gaussian, and if you change your domain and you go to time domain, you will still have it Gaussian with the same properties. Numbers will change, but the properties will be the same. So this makes it very strong. From a Gaussian, we change our domain, we are still Gaussian. So this is one of the very important properties that it has. These are the things that I mentioned. We define it by only 2 parameters, which are sigma and mu. And when we are plus minus 2 sigma, we have 95.4%, almost 96% of area covered. And then we are using Fourier transform. In other words, when we go from time domain to frequency domain, still the Gaussian is Gaussian. The Gaussian is a Gaussian. When we are calculating marginal probabilities, when we calculate the conditional probability, still Gaussian is Gaussian. So this is very good because we know the whole nature of the model. We know everything about this model. Of course, we said that it's symmetric around the mean. and sometimes the mean might be a big number. So then we are dealing with big number. So what people are doing in many of the books or lectures that I have put on the module, you see that we are using the term Gaussian distribution and normal distribution. But if you go to some probability courses, the term normal distribution has been used for normalized Gaussian distribution. So I'm using the word normalized Gaussian distribution, and I use also the term N for Gaussian, but we know that most of the mathematicians use different notation. Again, for us it's not important. None of us are mathematicians. We love them, but I mean, with distance. Now, what is about this type of normalized Gaussian distribution is this. Normalized Gaussian distribution is type of distribution whose mean is at 0, and everything is very nice. Because if your mean is 0, what will happen to this formula? Look, if your mean is 0, then you don't have this term. If you go to x squared, isn't it? So if I have the normalized Gaussian distribution, as you can see, I have no mu. Now, another important property that it has, the standard deviation or variance of this distribution is 1. So we get back into here. So we don't have it. We don't have the sigma. Mu. So it's x squared, and the sigma is equal to 1. So what happens? We will be left over with this distribution, whose x's are random variable and the other terms are all fixed. Now in probability books, they usually represent it by n, 0, 1. N, 0, 1. In pattern recognition books, we have it n, 0, 1, which means this normalized Gaussian distribution or standard normal distribution. And if we have n, mu, and sigma, you understand we need the general form. Now, which one is easier to manipulate, this one or the previous formula? This, because you don't have the sigma, you don't have x minus something. I mean, you might be very good. I mean, the computer can handle it, but I mean, it's easier to observe something in here. So the question is that if I have a Gaussian distribution, how can I convert this Gaussian distribution into a normalized Gaussian distribution or a standard normal distribution? In order to do that, we have a formula. We can convert a random variable into a new random variable who is n01. So z has n01 and x is whatever we have with some mean and some standard deviation. How can we calculate z? All our random variables should be subtracted from mean and divided by sigma. Again, in probability courses, if this course was a probability course, definitely we will show some examples about how you can do it, what are the challenges that you have, and if you have an exam, this could be a question in the exam. But here, for you, it's important to know that we can do this type of translations. Because you may open a paper, read a paper, or you open the textbook and you see that they have a Gaussian distribution with a mean mu and variance of sigma squared. And while they are doing some calculation, they suddenly turn into this normalized distribution. But you have to know how this distribution has came out, which now you know. Now, apart from the beauty of the Gaussian distribution, which is very natural distribution, it has several other important properties. And this important property is something which is, we call it central limit theorem. Now let's see what is a central limit theorem. Central limit theorem tells you that if we have infinity many distributions, like imagine you have infinity many random variables and each of them have different distributions. binomial distribution, Poisson distribution, Gaussian distribution, normal distribution, or all of them uniform distribution, doesn't matter. If we add all these random variables, in other words, if we add all this type of distribution, the result will be Gaussian distribution. So addition of infinity many different type of distribution is Gaussian distribution, and this is known as central limit theorem. This is very good. Why? Because I know all the nature of the Gaussian distribution, and if I have big enough number of random variables, I can easily get into Gaussian distribution. Now, I said infinity many. First, we don't have infinity many. So we correct the central limit theorem in the digital world. If you have lots of random variables, then the results will be Gaussian distribution. Now, next question is that what is the meaning of lots of? In our course, 30 or around 30 is large enough to say that the result is Gaussian distribution. Of course, we always use approximation, but we are happy with this type of approximation. Okay? That's why if you go to many image processing techniques, if you go to many pattern recognition techniques, you see that this Gaussian modeling is everywhere. Because we have the whole questions have now scenario has the nature of being estimated into central limit theorem. Look, many random variables doesn't mean that if we have big samples it is Gaussian distribution. If we have lots of samples, we have Gaussian distribution. If we have only 2 samples, but the samples are big, doesn't mean anything. So please be aware of that one. Now, we have talked about distributions, and as I promised you, for us it is very important to know, okay, I know I have Gaussian distribution. For this set I have this Gaussian distribution, mu1, sigma1. For this distribution, or this set I have Gaussian distribution, mu2, sigma2. But how can I discriminate them? How can I say that this data belongs to here and this data belongs to there? How can I say that what is the distance between these distributions? In order to find the distances, we have to review what are the distances that we know in general. Now, we are dealing with computers, and I can tell you that in pattern recognition, we owe a lot to the people who are working on information theory. Because soon you will see that most of the distances that we use have been driven by these people who work on the information theory. Why information theory? Because each pattern that we have, each set that we have, each cluster that we have, and we are giving a model, they have some information inside it. So people who work on information theory will give us a good way of representing this information so we can discriminate them better. Now, information, let's define what is information. Information has been defined by the famous entropy formula. If I have a PDF, each element of this PDF or histogram can be multiplied by the logarithm 2 of that probability, and the result of the addition will give me the information or entropy of that clusters, that image, or that set that we have. Now, information or entropy is always a positive number, which means that the result of this summation is always a negative number. And that's why that we will multiply it by minus. Why this is always a negative number? Those of you who have taken English processing last semester like Eric, they should know it because it was the same question that I asked. Yes, these are probability values, they are less than 1. They are even less than 1. But for us, it is important to see that they are less than 2. We know that logarithm of a number base n, if the number is less than n, it is always negative, isn't it? So this p, we know that p is positive, no question about it. So logarithm should be the term which makes it negative. And positive multiplied by negative is negative. We add lots of negative numbers. It is still negative, so we put We multiply also by a negative. So this is how we calculate the information or entropy of the sets that we have. Now, we have sets of clusters, we can calculate the entropy, but when we want to find out what is the distance between this point, there are two approaches. One of them is known as Euclidean distance, the other one is non-Euclidean distance. Do you remember Euclidean distance from geometry or, I don't know, calculus, some kind of high school mathematics? Euclidean distance between 2 points was this. If I had point x1, y1 and the point x2, y2, we remember to define distance, Euclidean distance d to be s square root of x1 minus x2 s squared plus y1 minus y2 s squared. Then maybe we did it like for multi-dimension. Sorry? Pythagoras. Yes, Pythagoras. Euclidean distance. This is known as Euclidean distance formula. Now, one thing important about Euclidean distance is it depends on the location. I should know what is x1, y1, x2, y2, x3, y3, z3, or whatever dimensions we have, and accordingly we can calculate the distance. So, some of the distances are known as Euclidean distances because they depend on the location. Some are called non-Euclidean distance. They do not depend on the location. Can you tell me that? What do you expect to see in the non-Euclidean distance? Give me a property which does not depend on the location. Information. Entropy. So here, that's why the information theory guys are helping us a lot, and we look at this non-Euclidean distance sets also today. Now, distance is kind of a method. When we say something is a distance in mathematics, it should have a special properties. In this course, if there are some mathematicians, it's high probably by the end of the course they will hate me a lot, because I will use lots of terms wrongly. And you will use it also wrongly. So did many other people use them wrongly. So these are the mistakes that we know. One of these mistakes that we do is we will call so many things distance, but they are not distance. They are absolutely not distance. They fail to prove the basics of distance. But they can help us to discriminate. So from our point of view, if you can discriminate, it means that you can introduce a distance. But we know they are not distance. That's why that we have this slide. So you can see some of these things that we call them distance are truly mathematically distance. Some of them are not. They might be divergence, but we use them as a distance. So we use the term distance, but we are aware that some of them are not distance. If some measure wants to be distance, it should need to have these properties to be true. Distance is always positive. If you calculate it negative, put absolute value. Distance between this point and this point, or distance between this information and that information cannot, -2 doesn't have any meaning. What is the distance between x and y? -2 meters. So what? It's 2 meters. So distance is always positive or 0. When do we have the 0? If we are at the same place. So if x and y are equal to each other, it means it is 0. IFF means if and only if. Now, a very important property in distance, which we fail a lot in so many of the terms that use distance, is this. Distance between Tallinn and Tartu is, let's say, 180 kilometers. What is the distance between Tartu and Tallinn? Is 180 kilometers. So it doesn't matter if you calculate the distance between x and y, or y and x, you will get the same results. So this is an important property of a distance. More important is this triangle inequality. Triangle inequality. But as you can see, for many of, I have written here, for many of the clustering techniques or distances that we use, again I use the term distance, but they are not, these third and fourth properties fail. any of these properties fail, it means it is not a distance. It can be divergence, which we will talk about them. It can be some other thing, but because it helps us to discriminate, we consider them in the category of distance. Now, very simple one. Minkowski distance of order P. How we calculated it? It is, again, it's Euclidean type because it depends on the location. Xi minus yi to the power of P. We add all the numbers to the root of P. And if P is equal to 2, we have the norm, L2 norm, the traditional Euclidean distance. If P is 2, what happens? We have xi's minus yi's, this point minus this point squared, and all the values have been added, and then a square root if P is equal to 2. We call also this Euclidean distance L2, or second norm. Second norm is important, so as first norm, L1, and norm infinity. So we will talk about these two norms also. But you know that if we change x and y, what will happen? Nothing will happen. In other words, this condition is true. So this is really, truly distance. Now, norm 1, L1, known as Manhattan distance, is basically x minus y. We put absolute and we add them. It's the simplest way of calculating the distance. It's like you take a ruler and you find a measure between the points. In the Google map, you can actually draw your path and then measure what is the distance, and it calculates basically the Manhattan distance. L infinity is actually kind of different. What I do, I calculate all the distances, if you know the points, and I pick up the maximum one as distance that I want. And we call it L infinity. So it is the maximum distance that I have. So if you want to calculate L infinity, or L infinity norm, in MATLAB, what you do, you just calculate lots of differences. You keep the results in a matrix or in a vector, and you calculate what is the maximum value. Now, another distance which here you can see covariance start to play a very important role, because we start to give weight, is something which I will always fail to pronounce it, and I call it Maha distance. So what happens here, this Maha distance that actually can be used in order to calculate later gain. We don't calculate gains, but some people need to calculate gain, so they always go to calculate the Maha distance, but it needs the inverse of the covariance. Do you remember when I showed you the slide of the covariance? I said inverse is playing a very important role, because apparently it is a very popular type of distance if you want to talk about gain. In other words, it's kind of weighted. When you assign different weights for different means and clusters. And in my opinion, the most popular one, at least the one that I use quite frequently, is something which is called Kullback-Leibler divergence. The name stands. It's not a distance, it's a divergence. Why it's not a distance? Because it fails the third and fourth property. But what we call it in pattern recognition, Kullback-Leibler distance, KLD. It's a good distance. It is very, very nice. It can help us to have the discriminations. But we know that this is not a distance. Let's see what it does and why it is not a distance. Now, it has been developed by people who are working on information theory. And it has been used in order to find the discrimination, the divergence of the information between one set and the other set. Now, the KLD between P and Q is calculated as P is the probability distribution function, Q is the probability distribution function. P multiplied by log 2 of P divided by log 2 of Q. Now, we know that this one is negative, this one is negative, negative divided by negative is positive, and multiplied by a positive number, the result is positive. So the result is positive, no problem. If P is equal to Q, let's see if the result is 0 or not. If P is equal to Q, what is the result?
1.
It's 1. It's just because this will cancel this one, and the addition of the P is equal to 1. What else? What will happen about the KLD of Q and P? Is it the same as KLD of P and Q? Look, KLD of P and Q is P log 2 of P over log 2 of Q, and KLD of Q and P is Q log 2 of Q over log 2 of P. Now you tell me. No. They are not the same. So as you can see, it is not a distance, but it is kindly give us a very good discrimination, and we keep it as it is. Usually P is what we have in the training, Q is what we have in the query. Now, it's not finished. As we will continue, in here, so we have seen what are the distances. What are the distances? We know that we have different type of distributions. We know the distances can be used in order to give us good discrimination. So we have enough tool in order to actually start now pattern recognition. So this is lecture 1, because we want to talk about this pattern recognition. What are the features? So quickly, I will review maybe the first 10 slides that you saw in lecture 1 of this course. And in those ones, if you remember, we talk about what is a feature, what is a pattern. We have talked about the definition of them. I showed you what is the curse of dimensionality. If we increase the features, number of features or size, we know that what is the problem. We will review it again. And in this journey, right now, we will start to talk about something which is called feature extraction. So we will talk about how to extract a feature. If we have lots of features, how to select them. Now, we have lots of features, and we are talking about feature selection. So the first thing comes like this. We have something like that, and we are choosing something like this. What is this operation called?
Extraction.
It means reduction. We have lots of features, but we need some of them in order to do our classification. So we will talk about how we can reduce our our data. We can reduce our dimensionality. We can select some of the features. Question: which features and why those features? Which technique will tell us which feature we have to choose? And how is it being guaranteed that it will be a good feature? So we will talk about those methodologies that we have to use in order to select our features. Now, I am sure you have seen this slide, so sorry to duplicate it. You remember we said that if we have lots of features, we put the features in a vector and we call it feature vector. Do you remember it? We said that all the features that we have, like I showed you about a fish or a bird, we said that we have colors, gender, color of feathers, I don't know, weight, size, and all those things, they can be features. And we put them all together in one vector, we call it feature vector. And we said that if we have n's of these feature vectors, they will make an n-dimensional space, which we call it feature space. So we have a feature vector, lots of these feature vectors come together and it makes them feature space. And we said that we can represent this feature space, these feature vectors in a feature space by using something which was called a scatter plot. A scatter plot, which you can't see, but if you have, you go to your model, you can see that there are lots of dots. It tells you that what are the concentration of different features. It helps you visually look and say that, it seems that if I am taking, let's say, the color of the bird, I can have a very good clustering among the birds. One problem. It's very good because human is involved. You look at it, you have lots of experience, and you can deal with it. The question is that how I can do it automatically. So we will learn how we can select these features. But in order to see scatterplot is something which you can use. I remember we talked about good features, bad features. And we will start, I gave you an example for the face recognition that, for example, hair, a style of the hair is a good feature or bad feature, and we agree that this is not a good feature, especially if you compare it with the location of eyes. So some of the features are very important, some of them are less important. How do we know that a feature is good or a feature is bad? What was the general definition of a good feature? What is the general definition of a bad feature? That's a correct word, but you have to say it in different form. Good feature results into the good recognition rate, but what is a good feature?
It can separate them.
Yes, correct. What do you mean by we can separate them? Good feature are those features that within class distance is small, between classes is very big. You can separate them very well. It results into the good recognition rate. So here, we can see this set of features are good because it seems that within this class the distances are smaller than the distance between the classes. Whereas here, it is not good. Why? Because within class distance with high probability is actually bigger than between class distances. So what will happen if I have something like that? How can I solve the problem?
It will be a very complex problem to solve.
Yes, but how can I solve it?
You need to find new features.
Change your features. Choose new features. These features are not good. Sometimes we don't change the features because this is the only feature that we have. Then what we do, we change the domain. Maybe from time domain we go to frequency domain and they will behave differently. So these are the things that you have to keep in your mind. Now, if you remember, we also talked about some of the features are good. We can linearly separate them. These are like the examples that I show in the class. Some of them are not very good. They are not linear or they are multimodal, like the examples that you see in the exam, which is like more complicated situations. Now, we talked about the correlation. Features can be highly correlated. Highly correlated features are like this. If you draw a line, you see that they are on the line. They have the same intensity. If they are increasing, all of them are being increased. Or if they are highly correlated with negative value, it means that if one of them is increasing, the other one is decreasing. But it is good because you can predict, you can understand, have a better understanding of what is the behavior of those features. Now, good features have, based on many textbooks, have several properties. Now, these properties are something like they have to be representative enough. Imagine we want to talk about face recognition, language. Is it a good feature?
No.
No, maybe language is discriminative enough, but it is not good enough to understand that someone is, let's say, Arab. So, it does not represent what we wanted to do. So, this representative depends on what is your application. And it should characterize what you want to display, what you want to represent. In other words, it should introduce a new meaning. Otherwise, we might have several features which are characterizing one thing. I'm trying to remember something like, I don't know, hairstyle, color of hair, length of the hair, and hairstyle. Maybe they are almost the same, so there is no need to have it. They don't introduce any new value or concept into a scenario that we have. We have to be able to interpret it. I give you some features. We have some scenarios, but I tell you that, okay, these are the characteristics that we have. These are the features that we have. And by having this one, you have to be interpreted. Why do you need to interpret the characters? If you cannot interpret it, you cannot simply make the probability model out of it. If you cannot make a probability model for your sets that you have, you cannot then go and define, let's say, discrimination functions, the distance functions. They have to be suitable, they have to be independent. Why independent? Why dependent features are redundant? Why?
Because they don't affect each other.
Independent when they don't affect each other. If they are very depending like this, if I have the x, I already know what is the nature of the circle. So introducing it will not introduce something much novel, because already I know about it. So, but if I have independent variables, independent features, what will happen? One will characterize one terminology, the other one will characterize something else. So they have to be independent. Dependency will introduce redundancy. We don't like it. Why? Because we said we want to learn how we can have the data reduction. And you will see one of the first things that the PCA doing, or so many methods do, is this. They go and calculate the rank. They tell me that which of the features are actually linear combination of the others, and we kick them out. Because if I know A and B, and I know that C is just addition of A and B, I don't need to carry C at all, because I can always produce it. Now, we also remember to talk about this peaking phenomena, which we said if we are increasing the number of features, it doesn't mean that we increase our performance. This is a real scenario. It's called drug screening, which was published in Bioinformatics in 2002. And they said that if they are increasing the number of features, actually it's a very good example, because you see significantly the performance drop. So after some point, increasing the feature, you cannot comment at all if it is good or bad. Sometimes it drops, sometimes it goes up. So this increasing the number of features is not good. Now, why increasing the number of features is not good? Because maybe we are introducing more dependent variable. Now, increasing more dependent variable, apart from this concept of being redundant, is this. Imagine this feature is a distinctive feature. It has its own characteristic, but it cannot discriminate very well. Okay? And I am introducing two more features, which are maybe depending on that one. In other words, they are maybe highly correlated. So what will happen? The bad one is start to get more friends. So it start to have higher power of making me to make wrong choice. So that's why that increasing the number of features may not always result in going up. May not result in order to go up. Sometimes, if you increase it, you will see that it will not change. Most of face recognition algorithms like PCA, those things that you see, it will come up to some point and it will stick at that one. Or it is slightly drop. But at some points, as you can see here, it significantly affects. Like from 82.3, you will drop to 70s. In the performance. Now, why data redundancy is important? Why do we want to reduce actually the dimensionality? Here are some numbers to help you in order to find out we are dealing with big values, big features. So we really need to reduce it. If we have an image of 1024 by 768, it means that we can have about 800,000 pixels, which each of them can be a feature. In bioinformatics, in genes and microarray data, it says that if we have a few samples, let's say only 100 of the samples, each sample can have dimensionality between 6,000 to 60,000. Multiply 60,000 by 100, it will be 6 million features for 100 samples that we have. For text recognition or text categorization, if we have a dictionary with 50,000 words, each word is one feature, so we will have 50,000 dimensionality, 50,000 features. Yes?
How do we know about face recognition? I mean, like.
No, multiply these two numbers.
So the pixels that are going.
Yes, 100 by 100 means 10,000 pixels. Each of them can be a feature. You see that we will spend quite some times, and we will have a homework on a method which is called Principal Component Analysis, PCA. We will talk about the details of that one. And you see, this is a method which actually tells us if we have this many features, how we can reduce this number into significantly smaller number and still get a very good performance. You don't need all these features in order to represent. So question is, how we can reduce the data, how we can reduce the dimensionality. Now, in order to reduce the dimensionality, we have to be able to select or extract these features, those important ones, those good ones. So we will talk about the techniques which we will use in order to do these operations. I told you that there are lots of terms that we use them wrongly, but it's just like we know and we use them wrongly, like distance. One of the other things that we do it a lot is this. You will learn in this course techniques which are very good for feature selection or feature extraction. So they are meant to be used for selecting or extracting, but we use them for recognition also. So I will introduce them as something which is used for feature selection, like Principal Component Analysis, but we use it actually quite a lot in recognition process. They are not meant to be used, but because they do good performance, why shouldn't be used? So lots of people are using them. You will also use it in your homework. Now, data reduction, which will stop here.